All right, so this problem says, suppose the ski patrol lowers a rescue sled and victim having a total mass of 90 kgs. So this is 90 kgs down a 60-degree slope. That's a very steep slope. Yeah. At constant speed. So he's being rolled down at constant speed. So let me remind you of the work energy theorem that you learned. So the net work done meaning the work done by all the forces acting on the object. So if there are 5 forces acting on the object, each force does work. And so if you add up all the work done, that's the net work done, is final kinetic energy minus initial kinetic energy. Okay, so what the statement is saying is slope at constant speed. So you're moving at constant speed, the kinetic energy is not changing, and so the net work done is 0. Okay, so that's what they're saying. Hey, dude, don't talk. The coefficient of friction between the sled and the snow is 0.1. Okay, so mu k is 0.1. How much work is done by friction as the sled moves 30 meters along the hill? So what we're going to do is, so there are several forces acting on the object. So for instance, this guy, tension, the friction force, and there's a normal force acting on this guy as well, except that since the displacement is in this direction, the normal force is not doing any work. But we'll calculate the work done by each force. Okay. So there's the friction force, and there's the displacement. Okay. So the work done by friction force is friction force times the displacement times cosine of the angle between the two forces. And the angle between the two forces is 180 degrees. Okay. So this is friction force d cosine 180. So friction force always does negative work. Okay. Friction forces always do negative work. Everybody understand? This is 180 degrees. Okay. All right, what is the friction force equal to? Friction force is equal to mu k times the normal force. And in this diagram, so there's the weight, there's the component of the weight. This is mg sine theta. This is mg cosine theta. Okay. So the work done by friction force is negative mu k mg cosine theta d. They gave you mu k. We know the mass of the object, person and sled. G we know, theta we know, d we know. Okay, so the work done by friction force and all that will work out in joules. Okay. All right, so friction force did that much work. All right, essentially what we're going to show you in this problem is we'll calculate the work done by all the forces, we'll add them up, and since you've already been told it's moving at constant velocity, we'll show you that the work done by all the forces will indeed add up to zero. Okay? So this problem sort of illustrates this work energy theorem. Okay? All right, so we've done the first piece. Then what is the second piece? How much work is done by the rope on the sled in this distance? So there's the rope is applying a force like that. And again, this guy is moving in this direction. So the rope is also doing negative work because the angle is 180 degrees, again, between the force and the displacement. Okay, so the work done by the tension, again, tension is in this direction and displacement is in that direction, is tension displacement times cosine 180. Okay. Okay, what is the tension equal to? The tension plus friction force is balancing that. Because this guy is not, he's going at constant velocity, he's not accelerating. This force is being balanced by the tension and the friction. Okay. So mg sine theta minus tension minus friction force equal to 0. That's the tension. Yep. All right, let's calculate that. Mg sine 60 minus 0.1 cosine 60. So the tension is 80% the weight of that person. Okay. Again, that makes sense. This is a very steep slope. Okay. So those guys have to be fairly strong to lower this patient. Okay. When would this be equal to the weight of the person?
Not on the slope at all.
All right. Very good. So, okay. And when would that tension be 0? Yeah, very good. Okay. So that's how I want you guys to. All right. So the work done by tension is negative 0.82 mg times distance. Okay, roughly 22,000 joules. Now, they ask you, what is the work done by the gravitational force on the sled? Okay, so there's the gravitational force, there's the displacement, and so you can do it one of two ways, and this angle would be 30 degrees, so you could take that times d times cosine 30. But you can also see that, okay, this force is the sum of this force plus this force. This force is not doing any work. This component is not doing any work. Why is that component not doing any work?
It's still loading on our
What?
screens.
We've gone back to that problem?
You already showed all this too, which is very strange. It's like you're showing it after I already showed this.
It's okay, it's an instant pullback.
That's the first time it happened?
That's the first time.
Yeah.
Just for some that's ever happened.
Well, let me know if there's a problem. I thought they fixed the problem, but. All right, so what we're trying to do is calculate the work done by gravity. Okay, so let me do another diagram here. So here's the slope. We'll represent the guy by a point. We want to calculate the work done by gravity. Okay, and so this would be 90 minus theta. And what you could do is, so the work done by gravity would be mg d cosine 90 minus theta. And cosine 90 minus theta is sine theta, so mg sine theta d. But you could have looked at it another way. Here's the other way to look at it. Mg is this component, which is mg cosine theta, and this is mg sine theta. This guy is not doing any work because the displacement is perpendicular to that force. So this guy is not doing any work. Only this guy is doing work because how much work he's doing, this guy is parallel to the displacement, is just that force times the displacement, which is that. Okay. All right, so that's the work done by gravity. So that is 90 times 9.8 times sine 60 times 30 meters. So work done by gravity is that many joules. All right, now we'll calculate what is the total work done. So the net work done is work done by gravity plus work done by tension plus work done by friction. Is there any other force? There's gravity, there's tension, there's friction, and what was not drawn was the normal force, so that's the other force. Plus work done by normal force. Work done by gravity is 22,915 joules. Work done by tension is negative 21,697. Work done by friction is negative 1,323. And work done by normal force is 0. Okay, and this should all add up to 0. Okay, so this added up to 105 joules. Okay, so it was all some sort of rounding error. Okay, that's close to zero. Okay, so that's the illustration of the work energy theorem. Okay. All right, so that is a long problem, but one part is there on the test. Okay. Okay, this problem says it takes 500 joules of work to compress a spring 10 centimeters. What is the force constant of the spring? All right. So this is x equal to 0. And when you stretch the spring exerts a force like that. And when you compress it, when it's compressed, the spring exerts a force like this. So the applied force has to be opposite to that. Okay? When you're compressing a spring. When you're compressing a spring, you're applying the force opposite to the force of the spring, and the spring force is given by minus kx. So this is equal to kx. The force you're applying is that. Okay, the work done by a force is given by this integral. So x initial to x final. So the force you applied was kx dx. And we will compress the spring by 10 centimeters from the origin to 10 centimeters. Okay, so from 0 to x final. So 0.1 meters. Okay. Yep. Negative 0.1 meters. You're compressing it to that. Okay. But they tell you how much work you did. You did 500 joules of work. So work done is 1/2. Okay, so 100,000 Newton per meter. That's a very strong spring. Yeah. 10 centimeters is this much, and you've done 500 joules of work. 100,000 newtons is, again, roughly, most of our weight is about 600 newtons. So let's say 1.5 person is 1,000 newtons. 150 people. So 150 people would have to hang on to the spring to stretch it 1 meter. Okay, so similar problem. A bungee cord exerts a non-linear What do we mean by a nonlinear force?
Force is changing.
So this force is a linear force, x to the power 1. So if you have a nonlinear force, you have a higher power or another power. So here is the spring constant, there is the Hooke's law part, and here is the nonlinear part. When you learn differential equations, you'll see nonlinear differential equations are hard to solve. Yeah. So anyway, there's a typo in this problem. So K1 should be negative 204 Newton per meter. Okay. And so when the initial stretches, mostly this term contributes, and when the stretch is large, then this term starts contributing. Okay? And there is the nonlinear term. Okay. So there's the coefficient of the nonlinear term. How much work must be done on the cord to stretch it 16.7 meters? Okay. So that is the bungee cord. The force that's applied by the bungee cord is this. And again, see, this has units of Newton per meter. The meter will cancel. And this has units of Newton per meter cube. Okay. So if the bungee cord applies, so here's the bungee cord. When you stretch it, it applies a force like that. The applied force has to be in the opposite direction. Yep. How much work must be done on the cord to stretch it 16.7 meters? You want to stretch it 16.7 meters. 16.7 meters is roughly 2/3 of the width of this room. Okay. So what the nonlinear term is telling you is, see, as you stretch it more and more, it's becoming softer. That's what this term is telling you. Okay. If it wasn't getting softer, this is the force you would have to apply. Okay. But here's a negative term, meaning it's getting softer. So if it was pure Hooke's law, this is the amount of work you would have to do to stretch it 16.5 meters. But since it got softer, you have to do that much less work. All right. So again, just doing integrations for a variable force. Okay, this says, how fast must a 3,000 kg elephant move to have the same kinetic energy as a 65 kg sprinter running at 10 meters per second? So that's roughly how fast a human can run. Okay, so the elephant is running that much slower than the human, okay, to have the same kinetic energy. Okay, at 15% the speed of the human. Yep. All right. Why can't the elephant run as fast as the human? What's that? Yeah, so you would need a lot of energy. So how much more energy would you need? 3,000 divided by 65, let's say. If that was 100, that would be 30. So that's roughly 50, 60 times the energy. You would produce 60 times the heat. Your cooling system would have to be 60 times more efficient. And whatever you're running after, it's probably not worth that much energy. It might be worth that much energy if you're running away from something. But then you're big and you can beat up on anybody. Okay. So I guess you're optimized for your environment. All right. Calculate the force needed to bring a 950 kg car to rest from a speed of 90 kilometers per hour in a distance of 120 meters, a fairly typical distance for a non-panic stop. That's a large distance. That's 60 miles an hour 120 meters is roughly 1.5 football field length, a little more than that. Yeah. So let's calculate the acceleration. V naught is 90 kilometers per hour. Okay, that's 1,000 meters. That's 3,600 seconds. So essentially, you divide that by 3.6. So your final speed is 0. Your initial speed is that. X minus x naught is 120 meters. Okay? So your deceleration is that. Okay, so your braking power is 27% the weight of the car. Okay, and of course the force would be so the braking force is 27% the weight of the car. Okay. Now, suppose instead the car hits a concrete abutment. So if a wall jumps in front of you and stops in 2 meters. Okay, so now instead of that being 120 meters, that's 2 meters. That's 60 times smaller. So the acceleration would increase correspondingly. Okay. So the acceleration would be 0 minus 25 square divided by 2 into 2. So if a wall jumps in front of you, you're experiencing 16 G's of acceleration. And that's not good for you. Okay. You know, sometimes at schools and stuff like that, the cops will have this set up where so you have essentially a track, and you sit on this track, and then you hit something, and they'll stop you. They'll do that at 10, 20 miles an hour, and you feel. Try those things if you ever get a chance. Yeah. Okay, this problem actually belongs to the next chapter, but we'll do it anyway, so you get a preview for the next chapter. Okay? A small block of mass, 200 grams, starts at rest at point A, slides to B where its speed is 8 meters per second, then slides along the horizontal surface a distance of 10 meters. 10 meters is from here to the wall. Okay. Before coming to rest at C. What is the work of friction along the curved surface? Okay, so friction is a non-conservative force. A non-conservative force just means the work done by that force is dependent on the path. So the work done by friction along this path is different than work done along that path. Okay, so work done by friction depends on the path, and that's a non-conservative force. All right, you learn all of this. So the work done by friction is mechanical energy final minus mechanical energy initial. Like I said, we'll talk about potential energy in the next chapter. So kinetic energy plus potential energy, and this is gravitational potential energy. What kind of work does friction do? Positive, negative, or zero? Negative. Okay. So friction decreases mechanical energy, and what does it do? It converts it to heat. Okay. All right. So this should come out to be negative. Okay. So at the start, it's starting off at rest. So initial kinetic energy is zero. They give you how fast it's going at the bottom, so they're giving you this. For the potential energy, we'll use this as the reference level. Okay. And so potential energy final is zero. Okay. So 1/2 mv final square minus initial potential energy is mgy initial. So the gravitational potential energy is given by that expression mgy initial. Okay. So that is the work done by the friction force. In going from A to B. The mass is 0.2 kgs, and it's going at 8 meters per second, minus 0.2 kgs, g is 9.8 meters per second square, times 4 meters. So as promised, the work done by friction is negative 1.44 joules. Now, what they ask you is what is the coefficient of kinetic friction on the horizontal surface? Okay. So what happened? It was going at 8 meters per second and it came to rest. And friction force acting in that direction stopped it. Okay, so now for part B, we'll draw the horizontal surface. Okay. and that was because there was a kinetic friction force acting in that direction. Okay. Let's first find the acceleration. Okay, you come to rest. You are going at 8 meters per second, and you came to rest over 10 meters. That's 64, half of that is 32 divided by that, that's negative 3.2 meters per second squared. So your deceleration was that, okay? All right, so friction force was the only force acting in this direction, and the acceleration was that. So there's the magnitude of the friction force is equal to mass times the acceleration. The mass cancels. So mu k so the coefficient of friction is 0.33 between that box and that surface. Okay, these are not silly problems. You see the mass canceled, and so what that means is, okay, as long as the surfaces are the same, you drop a box from here, that box will come to rest there. You know, Amazon and all those guys are interested in this sort of stuff. That's where the truck is waiting. Okay. You can have a 20-pound box or a 2,000-pound box. You don't want that 2,000-pound box to be moving at the end of the ramp. Okay. So you just got to make sure that the surfaces are consistent. Yeah. This is sort of a silly problem. All right, well, okay, we'll do a silly part. Yeah. So a person in good physical condition can put out 100 watts of useful power for several hours at a stretch, perhaps by pedaling a mechanism that drives an electric generator. Okay. So roughly the idea is you can work at 1/10 of a horsepower for several hours. And 1/10 of a horsepower is 75 watts, which is roughly this. Okay. How many people would it take to run a 4 kilowatt electric clothes dryer So 4,000 watts divided by 100 watts. So 40 people would have to bicycle to run your clothes dryer. So you want to have a greener footprint or a smaller carbon footprint, dry your clothes on a clothesline. Okay. What you also want is a washing machine that spins at a higher cycle and spins faster. Why? Or the squeeze cycle is faster. It squeezes out more water. Okay? And then you have to spend less time in the dryer. The man of the preceding problem consumes approximately that many joules of energy per day to maintain a constant weight. What is the average power he produces over a day? So that's okay. So power is energy over time. Okay. And we saw this in a table. Okay, so your energy consumption is in one day over a period of 1 day, 24 hours into 3,600 seconds. So this is how much energy you're consuming. This is how much energy you're consuming per second. So an average person is consuming 121 joules per second. Okay, so that energy is used to run various reactions in your body. Okay, and eventually, some of that is used to convert to ATP and stuff like that, but eventually all of that gets converted to heat. Okay. So that's how much heat you have to get rid of per second in your body. Okay. All right.